Hi grade 9s, we are going to get to start to become actual environmental scientists today, and we are going to start looking at how water quality is measured, monitored, and determine whether or not the health of a system is safe. So we're going to be looking at how we use our water, how we determine whether water quality is safe or not. We're going to learn what LD50 means. We're going to learn what parts per million are, biological monitoring, chemical factors, and then also dispersion and dilution. So we're back in Pleasantville. Pleasantville's been conducting water quality tests of the river over the past 20 years. Recently, they've noticed some significant changes in the quality of their water. If you have been hired as an environmental expert to determine why the water quality has begun to deteriorate. So to understand how the city has been conducting the tests is key to your understanding as to what's been going on. So first of all, you need to know how water quality is tested. So water quality itself is how pure a water sample is. It's determined depending on what you are using the water for. So drinking water have different guidelines than irrigation water. How do we monitor it? We look at two main factors. We look at biological monitoring and chemical monitoring. So when we look at the biological, we're going to look at the health of the aquatic organisms and determine the quality of water from there. If we're looking at the chemical, we're going to actually track the type and the amount of chemicals that are in the environment themselves. So we're going to start with biological monitoring. What does it mean to check the health of the water quality by looking at the health of the aquatic organisms? Well, there's four main groups of aquatic organisms that we can look at to determine the quality of the water. We have aquatic microorganisms. They are microscopic. You need to have a microscope to see them, and they don't have a backbone. You have aquatic invertebrates. They are not aquatic, and they don't have a backbone. Then you've got aquatic vertebrates that do have a backbone and are definitely large enough to see, and your aquatic plants. So let's start with aquatic microorganisms. Aquatic microorganisms, you need the microscope. They don't have a backbone, as I said, but they're like your bacteria. So E. coli is one of the ones that they talk about a lot on the news. They're viruses, they're plankton, and they're algae. And they kind of look super cool underneath the microscope. So what do they tell us? So if you have an increased concentration of bacteria, that can often be linked to a poor quality of water. What happens is if you've got this contaminant in the water, normally from human waste or animal waste and sewage, it'll cause an overgrowth of plants. When you have so many plants, they're going to die, which is okay in a normal environment because we need them to be decomposed, and that's how we recycle our nutrients. However, if there's too many plants or an overgrowth of plants, and you're going to have an overgrowth of the decomposers, which are going to use up all of the dissolved oxygen in the water, which will affect the fish and other water life. So aquatic invertebrates are our next big section, and these ones are the ones that they use a lot and are really kind of neat for us to look at because we can actually see them with our eyes. So they're not microscopic, they don't have a backbone, and there are things like insects, crayfish, crabs, worms, snails, clams, and mollusks. So in here I have some pictures of different ones, and if you look at the top, it says Group 1. These organisms are generally considered to be intolerant of pollution. So if you find the alderfly larvae, the Dobson larvae, the snapfly larvae, or the stonefly larvae, you are probably going to be in a very high water quality environment because they are intolerant to pollution. So they will be killed off in their larvae form, and you won't see them if the water quality is poor. That's how we can use our invertebrates to tell water quality. So here's another example and a little bit more information on how we use them. So they are our most abundant aquatic invertebrates. They're the easiest thing for us to test, and they tend to be the larvae. So they're kind of the squirmy, wormy, slimy ones. And larvae are the immature form of the insects. So they don't often have wings. They can, but they don't often. The larvae give you that indicator of the water quality because they are sensitive to pollutants. So some of them can only be found in high quality or excellent water quality. Then there's many forms that can be found in anything, and it wouldn't matter if it was high, medium, or low quality water. So we have keys that we use to do this. The image here is a picture of the key that we use. So again, if you look at the top group, these are the ones that are intolerant to pollution. So if you find them, you're going to have excellent water quality. Now group 2 tells you that they're maybe a moderate quality. And group 3, they're very tolerant. So they'll live whether there's good, fair, or poor water quality. So when you're looking at a water sample, and if you have a midge larvae, it doesn't actually tell you whether it's poor quality, moderate quality, or excellent quality water, because it could live in any of them. Whereas if you find a mayfly nymphs has to be excellent or good water quality. It cannot survive in fair or poor water quality. That's how we use those. So then we have our aquatic vertebrates. These have backbones. They're the ones that you think of when you think of who lives in the water. So there are fish, our frogs, our salamanders, our mammals, and our birds. Now, the best ones to use for water quality would be our frogs and our other amphibians. So they are used for water quality because they are the most sensitive to changes in their environment. So if we see an increase in mutations of our amphibians, then that would be a sign of poor water quality. Or if we see a decrease in the population of the frogs, would also be a sign of our water quality problem. Aquatic plants, they're required in large numbers for a healthy ecosystem. However, we do monitor them because, as we said at the very beginning, if you have too many plants or a sudden overgrowth of plants, you can also see that that has been, like sewage or fertilizer, has been dumped into the system and is going to cause problems in the future. So at this point, you can pause the video and go and answer those first 2 questions. I'm also going to make a video on how to answer them in case you're having any troubles. So our next type of monitoring is our chemical monitoring. This is where we track the type and the amount of the chemicals. It's really important that you know how dangerous a chemical is in the environment when you're doing this. So we measure the amount of pollution, and for that we use parts per million, parts per billion, parts per trillion. We measure the toxicity of the pollutant, and that's how we decide how dangerous the chemical is. And for that we use a term called LD50. And then what do we actually monitor? We just monitor dissolved oxygen, plant nutrients from fertilizers, pH, pesticides, heavy metals, and salts. So if we're looking at the amount of pollution, first of all, you need to know what pollution is. So a pollutant is anything that directly or indirectly harms a living thing. Pollution is an alteration to the environment that produces a condition that's harmful to living things. And parts per million is how you measure the pollution. So how many parts of that pollutant are present. So here again is that measuring the parts per million. So there is a toxin in this water sample, and you can see as you go from the bottom, 1 part per million, to 10,000 parts per million, there's a color change, and the color is showing you how many parts per million you have using a dye, so that you can see that the darker it is, the more it would have. 1 part per million is equal to 1,000 parts per billion, and it's just used to show you how much pollution is in the environment. So again, you can stop this video, watch the other video that's embedded, and then do questions 3 to 5 in your practice questions. Measuring the toxicity of a pollutant. So again, we need to know how we do that, and we need to know what we're even talking about. So toxins are any chemical that can harm a living organism. Toxicity is the ability, how easy it is for that toxin to harm a living organism. So this is measured in LD50. LD50 is a single dose or an amount that the chemical needs. That's clearly a spelling mistake there. That a chemical has given to a population, and it'll kill off 50%. I like to think of this as the Thanos snap. So the first year I taught this was when Endgame was coming out. So it was a huge, important thing in the whole world. And the Thanosnap had already happened. But LD50 is if you gave a population this chemical, with that percentage, 50% of them would die. So the first thing all of my students said was, well, it's a Thanosnap, and it's kind of stuck with me ever since. So it's measured in milligrams per kilogram, which means that milligrams of the toxin per kilogram of the living organism that you're putting it in. Now, I don't know if you guys have noticed this, but when you go to a doctor, sometimes they'll take out a calculator to calculate how much medicine you should have, and it's based on your weight. So how many milligrams you get of a medicine depends on how heavy you are as a person, because it depends on how you can react to it. So looking again at our LD50, we have that toxicity of various chemicals determining the safe concentration in the environment. So LD50 is measured in parts per million, parts per billion, parts per trillion. Parts per million is the most toxic of those three. So as you go parts per billion, that's less, and parts per trillion is even less. So extremely toxic chemicals we measure in parts per trillion just because they are deadly in such small amounts. Parts per million is used for less dangerous ones. And LD50 is normally determined by using mice instead of humans. We don't give a population of humans a drug and see how much it takes to kill 50% of them. That's not humane. But we do use mice, which we can argue is not humane either. But the other thing that has to do with it means that we need to use the LD50 as only a guide, because it really does depend on the species. And we don't really want to take a group of humans and test this stuff on them. So this gives you kind of a visual of LD50 is when you administer that toxin and half of them die. So it's giving you a graph form of that. But then it also tells you how much you would need for certain substances. So like table salt, you'd need 3,000 milligrams per kilogram. So per kilogram for a rat to just be eating table salt. Caffeine, you only need 192 milligrams per kilogram. And for DDT, which we talked about before, it's only 87 milligrams per kilogram. And all of those were taken by mouth. So the lower the LD50, DDT is much more toxic than table salt. So lower LD50, more toxic. Okay, last question on that sheet. You can go do that one. Which chemical factors do we monitor in the water? So we monitor dissolved oxygen, plant nutrients, pH, pesticides, heavy metals, and salts. So let's start with dissolved oxygen. Dissolved oxygen has an optimal amount of about 5 parts per million to support aquatic life. You can have 2 to 8 parts per million, but the best is about 5. Low oxygen levels can make it harder to support life because they're not able to take in enough oxygen from the water. High levels, on the other hand, also can become toxic. So your levels of dissolved oxygen in the water depend on temperature of the water. Cold water is better because you can get more oxygen in it. The turbulence of the water, how much it mixes up. You want to mix oxygen into the water. Photosynthesis, how much plants and algae are adding oxygen to the water, and then the number of aquatic animals. So aquatic animals use the oxygen, they don't add it back, so how much of that is there? So fertilizers, when we're looking at those, we're looking at our phosphorus and our nitrogen, and the reason why we look at them is because they can cause that overgrowth of plants in the aquatic environment, and when that happens, then when they die, you bring in all these decomposers who use up all the oxygen, and that bacteria that we talked about way back in the beginning of this video, that bacteria increase and they suffocate out the remaining plants and the animals in the water. This is called an algae bloom, and it happens a lot, actually. Plant nutrient populations generally come from untreated human sewage or the runoff of fertilizer fields. So that's the runoff from the fertilized field is what you're seeing in the diagram here. So we also look at our pH, our acidic, basic, or neutral. Now we're going to be talking more about acid rain later. We also do a lot more on just what acids and bases are. So normal rain and snow, has a pH of 5.6, which is on the acidic end. And with too much pollution in it, the acid rain actually gets much more acidic, and it can drop below 4.5. And when that happens, most fish are going to die off. Now you do have the situation where you've got the rain coming down and you've got a bunch of water in the lake already, but that acid again doesn't just disperse. It kind of sits there and eats away at buildings and is constantly around. So we need to be really careful about how much acid we are putting into the rain. The other thing that happens a lot, which happens especially in areas that have tons of snow, which is what we have here, is something called spring acid shock. So as the snow melts, the acid has stayed in that snow. So as the snow and the ice melt, and they'll release that acid into the water systems as they melt. And all of a sudden you'll have this spring acid shock where you'll have like a lot of animals killed off in the spring because of this hidden or trapped acid in the snow and the ice. The other thing that we monitor, of course, is the pesticides that we put on our different fields. So we talked a little bit last week, or I put it into our vocabulary, where we had pesticides, insecticides, fungicides, and some other sides. Herbicides maybe. And so that was just to give you all the different types of pesticides that we can use so that you kind of have the right terminology. The important part is that you know that even in small doses, pesticides can be extremely toxic. And the biggest problem we have for our water systems is that the farmers, the golf courses, and the cities all use different pesticides, and they all collect into that water supply, because they go through the runoff or through the groundwater and end up in our water supply. Heavy metals are another problem, and you guys have heard of this before. We'll talk about this with flint. So heavy metal problems would be things like lead, copper, zinc, mercury, cadmium, and nickel. And we've talked about this in the sense that, like, or at least I'm sure you've talked about it in the sense that like lead poisoning is bad, like lead in paint is bad, and lead pipes can be really bad for the environment. Because they're very highly dense, we've talked about mercury, when they're very highly dense metals, and they are toxic to all types of organisms. So we have these in our batteries, our tires, our gasoline, our paints, our thermometers, and even some fertilizers. And so we need to be making sure that we've got those contained or in a way that they are not going to be going and affecting our aquatic life, as well as all other life, of course. Salts as well can be a problem, especially, again, when you live in a place like Canada and it snows and we need to salt the roads. When we do that so that we can, save human life and make it so that we can drive safely in the winter and not have as many car accidents. And so we salt the road because when we salt the road, it actually decreases the freezing point, which means that it'll melt faster. But where does all that salt end up? So the salt goes into the water systems. And when it goes into the water systems, it's not good for aquatic life, but it's also not good for us to drink. So we need to be really careful with what we're putting into our water supply, is in general what we should be looking at throughout this whole unit. So this is kind of just an overall flow chart so that you can sort of think about how we look at water quality. So we monitor in parts per million and LD50, and we look at the biological factors, and we monitor the oxygen, salts, fertilizers, pH, heavy metals, and pesticides. It's kind of a good remembering tool. So how do we reduce the concentration of these harmful chemicals once they're already in the environment? So we know that some of them are already there. So what do? So we have some options that nature has done for us and some that we can help with. So dispersion, dilution, biodegradation, photoremediation, and photolysis. Phytoremediation and photolysis. So dispersion is just the scattering or the movement of the pollutant away from the source. So this can happen by the direction of the currents, prevailing winds, soil, how porous the soil is, and the properties of the pollutant. So if you have an emission in one area, it's going to spread out, and when it spreads out, hopefully it'll also dilute, and then it would be in a small enough concentration that maybe it's not going to affect any organisms. Fingers crossed. Dilution is when you've got that pollutant becoming less and less concentrated as it moves away from the source. So dilution and dispersion go together. So as they go away from the source, they become less and less concentrated because you've got it mixing with larger amounts of air or water or soil. So both of those help because sometimes the dose, obviously, not sometimes, but all the time the dose matters, which is why we have that LD50. Biodegradation is another way in where we have the breakdown of matter by living things. So we've got our scavengers, our decomposers, our worms, our algae, and our fungi going through and basically degrading all of these toxic chemicals. And so that's going to depend on a few factors as well, like gas exchange, temperature, moisture, pH, and nutrient levels for them to be able to optimally degrade for us. I'm not even sure. I think it's phytoremediation. I'm not entirely sure how to say that word. I'm not going to lie. I'm not really sure. But the first part means plant, and remediation is like your cure. So what happens is that the plants grow in contaminated areas. They absorb the pollutants up from the soil and the groundwater, and then they take the plant and they dispose of them, which also disposes of the chemicals. Now, this has happened in some super cool ways. So, this didn't turn out very well, but sunflowers are actually the international symbol for nuclear disarmament. So when you've got nuclear reactors or you're trying to get rid of toxic nuclear sites, what they do is they actually plant sunflowers because sunflowers are an amazing plant that is able to suck up the especially the nuclear waste in the soil and in the water supply there, and they can suck it up and then be removed, and they will clean up the area. Now, it's not magic, but it is really, really cool. So I've attached a couple articles, and I think we're going to do an article on this. You don't have to read both of them, but I found it very interesting that sunflowers can do this. So we'll talk a little bit more about this as well. But sunflowers are the symbol of cleaning up nuclear sites, which is kind of cool. So all around Chernobyl, they planted them, and they're still like harvesting to remove the chemicals, but they're still cleaning it up while they're there. Photolysis, I do know how to say that word. Photo means light, lysis means break down, so it's where the substance actually gets degraded just by being exposed to light itself. So just being out in the sunlight. Now, before we had all of these detergents and chemicals that we use to clean our clothes, most, and women, because that was tended to be their job, would actually just put stained clothes out in the sunlight, and sunlight will actually remove quite a few stains from clothing. So, not that I think you should stain your clothes on purpose. And it's super cold right now, so might not work very well because it's so cold. But in the summer, if you wanted to try that, if you had like a stain on your shirt that wasn't going away, go lay it outside in the sun, leave it for a few hours, maybe for the afternoon, then go out, and you'd be surprised how much the sun can actually get rid of just on its own. So again, another little flow chart to help you remember. So to reduce the concentration of chemicals, harmful chemicals in the environment, we use dispersion and dilution, biodegradation, phytoremediation, I'm not really sure how to say that one, and photolysis. So that will get us through for this week.